So today we're going to talk about implicit differentiation, which is basically implied differentiation. So far in the course, we have been taking derivatives of functions explicitly. And what this means is we can solve and isolate f of x, and then we just take the derivative of this, and we would end up with f prime, right, if we ddx both sides. Same with this, if we ddx both sides, we would end up with y prime is equal to something, right? So this has been, even if it's a difficult derivative, we still can do it, okay? So the thing is what about a function like this? What can we do when we're dealing with functions where we cannot, what can we do with functions where we cannot solve for y? So if you notice, I could try to maybe factor out a y, but then I'm left with this cosine of y over here. And how do you get a y outside of the, or get it out of the argument of a cosine? You have to arc cosine it. But in order to arc cosine it, you're going to then have to arc cosine both sides, and you'll put some more y's inside of an arc cosine, which is worse than what you started with. So basically, these types of problems, we cannot solve for y, and we cannot solve for f of x. So how would we find y prime if you can't isolate y prime? Or if you can't isolate y. So what we do is we do something called implicit differentiation. And implicit differentiation is a good tool that's going to help us work with problems that cannot be solved for y or cannot be solved for f of x. Now, the big thing with implicit differentiation is the chain rule. The chain rule is very, very important in implicit differentiation. Now, here I want you to notice something. I'm asking you to take the derivative of f of x cubed. Now, the problem with this is I have no idea what f of x is. Okay, I have no clue what it could be, but I know that if I want to take the derivative of it, I'm going to have to take the power, put it in front, rewrite the inside, reduce the power by 1, and then attach the derivative of the inner function. So this would be f prime of x. So as you can see, I found the derivative, right? I said that f prime of x is worth that. Now, f prime of x is, or I shouldn't say f prime of x is worth that. What I've done is I have found the derivative of f of x cubed, okay? Let's take a look at this one, okay? Let me see, if I take the derivative of this, I would get 2x, rewrite f of x, and what I'm doing is I'm just calling this my u and that my v. And so I'm gonna have, this will be, once again, u prime v, and then I'm gonna do plus u v prime. Okay, so plus, now what's the derivative? Okay, we rewrite the u, and then the derivative of f would be f prime of x. So notice we have our derivative, and we could factor out an x and everything, but we're not kind of doing that right now. We're just trying to worry about trying to see and be comfortable with taking this derivative of f of x that's embedded within another function. So, and again, this is basically just the chain rule, right? We're just going to do the derivative of cosine, which would be negative sine f of x, and that would be normal. But because it's not a plain old x, we have to attach the derivative. Remember in a previous video, I said if you want, you could call this u. So then this would be, we have to attach u prime at the end right here, right? So what's the derivative of f of x? Times f prime of x. Okay, so this is letting us take the derivative of something without actually knowing what is the function we're dealing with. And one last one just to get some more practice. This will be the derivative of tangent is secant squared of x f of x. But that would be the derivative of tangent. Now we have to attach the chain, and that would be the derivative of x is 1, rewrite f of x, plus rewrite x, the derivative of f of x is f prime. So if you notice, I have been able to take the derivative of all of these functions, and I never even knew what f of x was. So we're going to use similar thinking to solve for f prime. So in this problem, I'm going to ask you to find f prime of x if 2f of x is equal to x squared plus sine of f of x. So what I need to do first, is I need to say, okay, I'm going to ddx both sides. So I'm going to ddx 2f of x equals, and then I'm going to ddx x squared plus sine f of x, okay? And then we have that. So when I take the derivative of 2f of x, I'm going to get 2f prime of x, right? Because it's the constant multiple rule. When I take the derivative of this, I'm just going to get 2x. And remember, these are all with respect to x. These are derivatives with respect to x, okay? When you're using Leibniz notation, whatever the denominator is, in the ddx. If it's ddy, ddg, ddm, whatever the denominator is, that's with respect to, okay? So now we're going to have the derivative of sine is cosine of f of x, but I just took the derivative of cosine of something other than plain old x, so I must attach the chain f prime, okay? Now that would be technically correct, but the problem is I asked you to find f prime. So what you do in this case is you get everything with f prime on the same side. So I'm going to subtract cosine f of x times f prime of x. Okay, and I'm going to subtract it to this side as well. Cosine f of x times f prime of x. So that means and again, I'm probably writing out, you could probably do this step in your head, but I'm just going to write it out. 2 f prime of x minus cosine of f of x times f prime of x equals 2x. So now what I have to do is I notice that this and this both have an f prime. So what do you do when two pieces of addition or subtraction have the same thing in common? We're allowed to factor. So I'm going to factor out f prime. And what does that leave behind? That leaves behind a 2 minus a cosine f of x, right, equals 2x. And then you guys know from here, pretty straightforward, we divide by 2 minus cosine of f of x divided by 2 minus cosine of f of x, okay? So then our final answer is f prime of x, and remember these canceled, right? They became 1s. And we have f prime of x is equal to 2x over 2 minus cosine f of x. Let me just double check my answer, make sure I don't make any silly mistakes. 2x over 2 minus cosine of f of x. Yep, that's it. So this would be my answer. So notice what I did was I solved for f prime of x. But now notice the reason I needed implicit, I kind of jumped the gun on this, I should have explained it, is I need to get f of x alone. So if I try to get f of x alone, because if I have f of x alone, then I can just ddx it and I'll get f prime of x, right? And then, you know, whatever's over here will be my answer, okay? But the problem is I cannot get this f of x out of the sine function without messing up the other side and also this as well, okay? So it would be very difficult to, or actually might be impossible to get the f of x out of the sine function argument. Okay, so whenever you run into that, but somebody still wants you to find f prime, you probably have to use the technique I'm using here. Okay. All right, so let's look at another one. All right. Let me see what else I got. So we could look at find f prime of x if f of x squared plus 3x e to the x equals e to the x times f of x. Now, once again, we're going to run into trouble here. It's going to be really hard to isolate f of x because the moment I subtract e to the x, f of x over to the other side, I could factor out an f of x, but then I also still have an f of x inside the parentheses when I factor. So that won't get me to where I want to go. I'm still going to have an f of x floating around that's not separated, or I'll have more than one f of x floating around. So I can't solve for it. So what I'm going to do is I'm going to do implicit differentiation. Once again, I'm going to ddx this, and I'm going to ddx this. Okay, so let's see what we get. So the derivative of f of x squared, take the power, put it in front, rewrite the f of x, then attach or reduce the power by 1, and then attach the derivative of the inside function. Okay, so that's what I did. So take the power, put it in front, that would be this guy, reduce the power by 1, so that's why it's a 1 now, and then attach the chain. Rewrite the inside, reduce the power by 1, and then attach the derivative of the inner function, which would be f prime. Now I have to take the derivative of this, but this is a product rule. So this is going to be 3e to the x plus 3x e to the x equals, oh, another product rule. Great. E to the x f of x. Let's see here. E to the x f of x plus, rewrite e to the x, the derivative of f of x is f prime of x. So we got a lot going on this problem, but I know I have an f prime of x here and I have an f prime of x here. So they need to be together, okay? So what I'm gonna do they need to be on the same side of the equation, is I'm going to subtract e to the x f prime of x minus e to the x f prime of x to both sides. So that's 0. And then I also need to subtract 3e to the x minus 3x e to the x. And then I have to put it over here as well. Minus 3e to the x minus 3x e to the x. So that and that becomes 0. Okay. So now what I'm left with is 2f of x times f prime of x minus e to the x f prime of x equals e to the x f of x minus 3e to the x minus 3x e to the x. Wow, that's a lot. Let me double check. Let me go over everything and make sure I didn't mess anything up. So minus 3e to the x minus 3x e to the x, and then e to the x times f of x. I think that looks good. Okay, so now we're back to where we were in the previous problem. We notice that we have an f prime here and an f prime here. So what I'm going to do is I'm going to factor out f prime of x, and that'll, oops, sorry, not an equal sign, and that'll leave me with 2f of x minus e to the x. And that equals, now these guys all have an e to the x, so I'm going to factor this out. Maybe that'll help me clean up at the end. And now I have to divide everything by 2f of x minus e to the x. That cancels and becomes 1. Divide this side by 2f of x minus e to the x. And let's see what we got left standing here. F prime of x equals e to the x f of x minus 3x minus 3 all over 2f of x minus e to the x. And I guess there is nothing I can clean up. Yeah, so factoring out that e to the x turned out to be no good for anything. It didn't help us at all, but at least I knew that if I had to cancel an e to the x somewhere, I could have. Be sure you guys do not cancel those. That is not legal. You are not allowed to do that. Remember, because it's plus or minus in your denominator. So that would be our answer. And once again, the derivative is defined in terms of f of x, okay? So again, this is why we needed implicit differentiation, because the only way I could find the derivative of f prime is to write it in terms with with x's and f of x's. So that's why, once again, this is called implicit differentiation. Okay, now let's see what else I got. Let me see here. Oh, this is a hard one. Okay, so give this one a shot, guys. I'm going to pause the video, have you guys pause the video and try this one. So this one says find y prime if 2xy cubed plus y squared equals cosine of x plus y. Okay, so now I'm going to switch to y instead of f of x. Switching to y just makes the notation a little bit faster to write. So all those times I was using f of x, I could have called it y in general, and instead of calling it f prime, I could have called it y prime, and it would have just saved us a little bit of time. And again, you know, kind of keep track of what variables they're using from problem to problem. But I want you guys to pause the video and try this one without me telling you how to do it. Make sure I wrote this correctly. 2xy cubed plus y squared equals cosine x plus y. Yep, this is it. Pause the video, give it a shot, and try to solve for y prime. Okay, so the first thing you guys should have been doing now that you're back from pausing is you should have ddx both sides. Okay, so now when you do that, you have a product rule. So yeah, don't forget your product rules. Just because you're so worried about implicit, you're forgetting all the other stuff you already know. This will be 2y cubed plus 2x. Now, what's the derivative of y cubed? Wouldn't it be 3y squared? That would be what it normally is. But remember, we're taking the derivative of y with respect to x. So that's going to leave us with a dy dx. But dy dx is really just y prime. Okay, so what would the derivative of y be with respect to x? It would be y prime, okay, or dy dx. Plus, now what's the derivative of y squared normally? Well, this would be 2y. So that would normally be it, but the problem is this is with respect to x. Remember, I'm doing ddx. So technically, I would be left with dy dx. But we know that dy dx is really y prime. Once again, just for notation to have it all the same. Okay, so now the derivative of cosine is negative sine, and then you have to rewrite the inside, right? Because the chain rule says take the derivative of the outer function, negative sine in this case, rewrite the inner function, x plus y, and then attach the chain rule, or I shouldn't say the chain rule, attach the chain. So the derivative of the inner function, which would be 1 plus y prime. Remember, the derivative of y is not 1, it's y prime because we're doing d dx to everything. Okay, hopefully that makes sense. If you're having trouble with it, talk to me about it in class or during office hours. Now we have a real problem. We have 3 y primes and one of them is embedded inside a parenthesis. So hopefully what you guys did was, the secret to this one is you distributed the sine function of x plus y to both of those. So now you have 2y cubed plus 2x, or let's call it 6x y squared y prime plus 2y y prime equals negative sine, you know what, I'll write it like this, negative sine x plus y. So that was 1 times negative sine x plus y, but now we have to do minus y prime times sine x plus y. Okay, so all I did, you guys, was I just distributed. I just took sine times 1 and sine times y prime, okay, or the sine function of x plus y. So I just distributed like that, okay? Now, when we look at this, we have a y prime on both sides. We actually have 3 y primes. So I'm going to move this guy, plus y prime sine x plus y, plus y prime, let me write it right here, plus y prime sine x plus y. And then I have to, and this becomes 0, right? And then I have to subtract 2y cubed. That becomes 0. And I'm going to subtract that over to here, 2y cubed. So let's see what's left standing. We have y prime sine x plus y plus 6x y squared y prime plus 2y y prime equals negative 2y cubed minus sine x plus y. Wow, this is a rough one. I told you this one's tough. Okay, now the job now becomes the same as last time. It's just a lot of writing, but it's to factor out the y prime. So I'm going to write y prime right here. And this is going to leave me with sine of x plus y plus 6xy squared plus 2y equals negative 2y cubed minus sine x plus y. And then just like before, it's ugly, but we just divide. Sine x plus y plus 6xy squared plus 2y, sine x plus y plus 6xy squared plus 2y. Let's see here. So these will cancel and become 1. So we have y prime equals, now I think, I don't want to mess with that negative sign. Who cares? I guess I'll leave it. So negative 2y cubed minus sine x plus y all over sine x plus y plus 6xy squared plus 2y. And that would be it. That's a nice, easy one, right? Just kidding. That's a rough one. Anything when you have products and quotient rules and you have chained sine functions with extra stuff inside the sine function, it just becomes a little bit more difficult in general, okay? All right, let's see another one. So let's find the equation of the tangent line to the curve y squared minus 4x squared y equals negative 3 at the point negative 1 comma 3, okay? So what we're going to do is we're going to do everything the same as before. Remember, find the equation of the tangent line is math code for find the derivative, and then use that to, or that's your now slope of your tangent line, and then use that to create the equation of the line. So I guess we're just going to ddx everything, right? So let's just ddx this, and let's ddx this, take the derivative of both sides with respect to x. So then this will become 2y minus, now do you guys see the mistake I made? What's the mistake I made? I took the derivative of y squared like it was normal, but it's with respect to x. So technically that becomes dy dx, but I want to write cleaner and faster notation. Leibniz notation is actually better in a lot of instances, but for speed, just writing y prime is better. And then now we have minus. I'm going to put parentheses around this minus, the minus sign, so I remember to distribute it. And then I'm just going to do the product rule. So this would become, let's see, the derivative of 4x squared would be 8x, rewrite the y, plus 4x squared y prime. And now the derivative of the other side is 0. Okay, the derivative of -3 with respect to x is 0. So now let me see here. Let me distribute 2y y prime minus 8xy minus 4x squared y prime equals 0. Let's move the 8xy out of here. And let's see what we got left. We have 2y y prime minus 4x squared y prime equals 8xy. So now I know I'm kind of back to where I've been doing these problems. I start, or back to where the original problem started, where I had to factor out the y or the f prime. So now I'm factoring out the y prime. And then I'm going to divide both sides, just like I've been doing. That becomes 1. So now we're left with y prime is equal to 8xy over 2y minus 4x squared, okay? And if you leave that, you get marked wrong because that is not what they asked for. That is the derivative. They asked for the equation of the tangent line. So what I'm gonna do is I'm gonna find y prime of, and the point they gave me was -1, 3. I'm gonna find y prime of -1, 3. So I'm gonna plug in -1 for x and 3 for y. And let's see what we get. That would be what? -24 over, that would be 6 minus 4. So we get -24 over 2, which is -12, I believe. So now we have our equation of the tangent line becomes y minus 3 equals -12 times x plus 1. And that would be my equation. Now, if the computer wants it in y equals mx plus b form, you could then do y minus equals -12x minus 12 plus 3. So y equals -12x minus 9. That would be in y equals mx plus b form. Okay. So far, so good. Not too bad. All right. So let me see here. I think I want to develop, I want to show you guys a few new formulas. Your homework is a little bit, the book that I switched to for this semester isn't as focused on some of this stuff until chapter 7, but the book I normally teach out of, called With Early Transcendentals, normally wants you to learn a lot of these ahead of time. So what I'm going to do is I'm going to teach you some of the like basic ones. So we're going to add 2 new formulas. Okay, so the first one is find the derivative of y equals sine inverse of x, okay, using implicit differentiation, okay? So we have to kind of think. So basically, we want to know the derivative of y equals sine. So I want to know y prime and then whatever the derivative of this would be, okay? So we're going to ddx both sides. But we have to think about, what does sine inverse of x equals y actually mean? So this actually means, or let's write this, y equals sine inverse of x, or arc sine. This actually means, I want to write it like this. X equals the sine of y, okay? So remember, an arc sine is just asking you for what angle would have created this relationship, okay? So instead, normally with trig, when you're finding the sine function, you take the sine of an angle and it creates this relationship between side lengths. Well, the arc sine is saying, I'm giving you the side lengths, what angle would have made it happen? Okay, so it's just working backwards, okay? So, and we're gonna stay restricted between negative pi over 2, oops. And we'll just restrict it for that. So we're gonna take a look at x equals sine of y, okay? So I'm just gonna write x equals sine of y, and let's go from here. Let's take the derivative of both sides. So I'm gonna ddx both sides, okay? So now that will become 1, right? Because the derivative of x with respect to x is just 1. And then this will become the cosine of y, but then we have to attach the y prime, the inner function, okay? So remember, we're trying to solve for y prime, so that's great. I like what's happening here. So I'm gonna divide cosine of y over to the other side, so we end up with cosine of y is equal to y prime. So I'm feeling pretty good so far, so I have y prime. So the problem is I want everything in terms of x's, right? So I have to find some substitution or some way to manipulate this to get stuff back to x, to get stuff back to what I'm working with. So one thing, whenever you're dealing with sine, cosine, or sine and cosine, a very common thing is the Pythagorean identity. So sine squared of y plus cosine squared of y is equal to 1. We know that fact, okay? So what if I were to solve for cosine of y? So we would have cosine squared y is equal to 1 minus sine squared y, and then I could square root both sides. So I'd have cosine of y is equal to the square root of 1 minus sine squared y. Now I know there's supposed to be a plus or minus, but we're gonna deal with the positive version for this problem, okay? So that's interesting. So that means I can now replace cosine of y with 1 minus sine squared y. Okay. Now, that's a little bit strange to think about, but it almost feels like I made the problem worse. But I'm going to write this. I'll come down here. So I'm going to say that 1 over. So 1 over, now y is now worth 1 minus sine squared y is equal to y prime. Okay. So that may not seem helpful. Okay. However, go way back to the beginning. Didn't we say that this implies that x is equal to sine of y? And I see a sine of y right here. It just so happens to be sine of y squared, or sine squared y. So what I'm going to do is I'm going to replace the sine of y with x. So this will now become 1 over the square root of 1 minus x squared equals y prime. I now have my formula. Okay, so the two new formulas, and we remember the whole goal was we want y prime. I want to know y prime, and I found it. Okay, so our goal, and you could do the similar thing with tangent. So the two main ones I'm going to focus on, there's technically all 6 of them, but the two that I'll probably test you on, and sometimes I might throw homework in for cosine or for arc cosine, but in general, the two new formulas, so I know I have it written above, but this is where they're actually going to be. You know what? I'll write it in red. Are the derivative of sine inverse of x, equals 1 over the square root of 1 minus x squared. And then we also have ddx of sine, well, not sine inverse, tan inverse. And this one is just 1 plus x squared. And I'm not going to go into that one, but you guys can memorize these formulas or write them next to you have them in your notes when you're taking the exam. These will be the two I'll focus on. Now there is 6 of them. There's for each one arc sine, arc cosecant, arc secant, arc tan, arc cosine. But these will be the two that I kind of focus on in this course. Okay. So let's take a look at an example. Find the derivative of y equals tan inverse of 4x cubed. Okay. Now notice this is just for tangent of x. So somebody came along and messed it up and they put a 4x cubed in there, but we know how to deal with that. That's the chain rule. So what I'm gonna do is I'm gonna say y prime is equal to, now it says that if you wanna take the derivative of tan inverse or arctan, you just do 1 over 1 plus x squared. But the problem is we don't have plain old x squared. We have 4x cubed. So I'm gonna do 4x cubed squared. But I still never took the derivative of the 4x cubed. So I have to attach the chain rule, which would be 12x squared. Hopefully you guys all see that. Remember, you could, even if you wanted, you could call this u once again. So this would be 1 over 1 plus u squared times u prime, if you want to think about it that way, okay? So now when I do my cleanup, this would become 12x squared all over 1 plus 16x to the 6th. And that will be how you could take the derivative of an arctan function. Okay, so let me take a look at another one. Let me give you guys another practice problem. What if we said y equals sine inverse of the square root of x? Okay, so once again, we want to rewrite this, and I say find y prime. Okay, so the first thing I'm going to do is I'm going to rewrite this sine inverse of x to the 1/2. Once again, I prefer everything to be powers instead of radicals just because it's easier to work with. So then if I want to take the derivative, I'm going to get y prime equals, now we go up here, what's my derivative? 1 over the square root of 1 minus x squared. So 1 over the square root of 1 minus x to the 1/2 squared. So that would equal 1 over, oops, hold on. Now notice, once again, this is my u. This is my u. That's not plain old x. If it were plain old x, this would be the answer, and I'd be done, okay? But it's not plain old x. It's x to the 1/2. So I have to attach the derivative of x to the 1/2, which would be 1/2 x to the negative 1/2, okay? So now let's see what we got here. So we now have 1 over 2 x to the 1/2 times the square root of 1 minus, what would that just be, x? So that's technically the right answer, but notice they're both square roots. This is technically a 1/2 power, and this is technically a 1/2 power. So more than likely, you're going to be asked to clean this up, and you're going to be left with 1 over 2 times the square root of x minus x squared. And I believe that would be the answer they would probably accept in your homework. This one is fine, but it's just not simplified. This one is just basically saying you know how to do the derivative, but you don't know how to simplify, okay? So I'm pretty sure that's the answer they're gonna wanna end up with in that particular problem. Okay, let me see. I think that's gonna do it for this video, guys. I mean, we can try a few more problems in class if you want, but I think that's a good start for you to get going on implicit differentiation. So thanks for watching, and let me know if you have any questions.